Okay, so in this second section of the chapter on martingales, we will discuss stopping times and optional stopping theorem. And then we'll look at some applications to random walks. So let's start with the definition of stopping times. Again, we consider some probability space. And here our index set will be just the natural numbers. And here we'll start from 0 for convenience. Now we'll again consider an increasing sequence of sigma algebras indexed by these integers. So we'll have sigma algebras Bn, which increase as you go up the sequence, and all of them are inside sigma algebra B on our probability space. Then the definition of a stopping time is as follows. Okay, so the stopping time, it can be defined not only for martingales, but it's defined with respect to this increasing sequence of sigma algebras. And a random variable tau on this probability space, which takes these integer values 0, 1, 2, and so on, is called the stopping time if the event that this tau is less than or equal than n, this event belongs to the sigma algebra Bn for all n greater or equal than 0. Now, equivalently, you can ask that tau equals to n belongs to Bn, again, for all n. And of course, the equivalent here, it just comes from the fact that you can write the event tau less than or equal than n as a union from 1 to n of the events that tau is equal to k. And each of these, if it belongs to bk, because the sequence is increasing, your union will also be in Bn. And in the other direction, you can write the event tau is equal to n as tau is less than or equal than n minus tau is less than or equal than n minus 1, right? And if you assume that these are in Bn and Bn minus 1, again, by the increasing property, this difference will also be in Bn. So both definitions are equivalent, and what it means is that if you think of looking at this sequence of sigma algebras as encoding some kind of data, you decide that you stop at time n just by looking at the data up to that time. So this event that tau is equal to n is measurable with respect to the sigma algebra. Okay, maybe let's give an example. First, of course, we have already seen examples of stopping times in one of the previous chapters. But here, if we look at the sequence of random variables which are adapted to this sequence of sigma algebras, then, for example, you can take tau to be the first k when your sequence xk exceeds some value, let's say greater or equal than 1. Right? Then this will be a stopping time, because the fact that tau is less than or equal than n just means that one of the x's up to n exceeded 1. Right? So you can write it as a union of events that x naught is greater or equal than 1 up to xn is greater or equal than 1. And since you assume here that xn's are adapted to Bn, right, this first event will be in B naught, and so on. This last event will be in Bn, and because of the increasing assumption on the sigma algebra, this union is in Bn. Okay, so of course you can construct many other examples. Basically, if you have a sequence of random variables, you can consider sigma algebras Bn generated by them, and then define any kind of decision rule how you stop by looking at the values of your sequence according to the rule that looks only at the values up to that time. And you can, we'll look at many of these. Right, once we have this definition of the stopping time, another important definition that is associated to it is a sigma algebra of all events up to the stopping time, or sigma algebra of events that depend on our data up to that random stopping time tau. This is defined as all measurable events such that the part of your event on the event that stopping time is less than or equal than n is Bn measurable, or is in Bn, or it depends on the data in the sigma algebra Bn. And this is true for all n, for all integers. Of course, equivalently, again, you could say that the part of your event B on the event that you know that the stopping time is equal to n should be in the sigma algebra Bn. Okay? So this kind of formalizes all events that depend on the data up to the stopping time tau. Now, once you define all these events that depend on the data up to a stopping time, you can check the intuitive statements like the fact that the random variable x tau is measurable with respect to the sigma algebra, or the sum of your random variables up to the stopping time is measurable with respect to sigma algebra. So these two will be b tau measurable. Okay, where of course I'm still in the previous setting, assuming that our sequence x is adapted to the sequence of sigma algebras. Right? So anything that you express up to the stopping time in terms of these random variables, it will be measurable on this sigma algebra. And of course, the way you check this is by saying that, well, let's say y x tau is measurable. You have to check that any event of the form x tau less than or equal some constant is in this sigma algebra. Right? That's what this measurability means. And by definition, you have to check that when you take a part of this event intersected with either tau less than or equal than n or tau equal than n, this should be in Bn. And of course here, if you know that tau is equal to n, this is the same as xn is less than a constant intersected with tau equal to n, right? And then it just follows from our assumptions that the first set is in Bn because we assumed xn to be Bn measurable, right? And this is also in Bn by the definition of the stopping time. So this intersection is in Bn. And similarly, if you consider any kind of function defined in terms of your x's up to tau, as soon as you fix the value of tau, you're basically looking at the function of x's up to that time, which is Bn measurable. All right, so our interest in stopping times is kind of twofold. So first of all, it's an interesting and important definition on its own right. So for example, when we discuss the optional stopping theorem in a second, this is just an interesting result by itself, and the stopping time is just a natural part of the result. So we'll discuss it in a second, but the importance of stopping times is also more technical. So for example, in the next section, when we prove inequalities for martingales, they can all be proved without any reference to stopping time or without any definition of stopping time, but the stopping times just conveniently express many events of interest in a natural way. And so once you summarize the properties of stopping times, you don't have to repeat the same argument over and over again. So it's simply a convenient packaging. When you deal with sequences of random variables, stopping times just come up naturally in many situations. And so as a result here, we begin by proving a number of important properties of the stopping times. Okay, well, let's start with some very basic ones. For example, if you take a non-random, just a constant tau, then of course it will be a stopping time. And the sigma algebra will be just Bn. Now, above I already gave one example that x tau was measurable with respect to the sigma algebra B tau, but let's also mention here that the tau itself is measurable with respect to the sigma algebra. And how do you prove this? Well, again, you want to check that the measurability of a random variable just means that any level set tau less than or equal to some constant. Now here tau is integer, so we can just take an integer constant k. We want to check that this belongs to this sigma algebra. And how do you check? By definition, this means that the part of this event intersected with the event that tau is less than or equal than n should be in Bn. But of course here it just means that tau is less than or equal than the minimum of k and n, right? Which by definition of a stopping time means it's in B with the index minimum of k and n, and by inclusion, of course, this is inside Bn, and so you get exactly what you want. Another property is that tau is a stopping time if and only if tau greater than n is in Bn for all n. Right, so this is just as a trivial observation as the one we did above, right? Because if you look at tau greater than n, this is just a complement of the event that tau is less than or equal than n. And so if one of them is in sigma algebra, then the other one is in that sigma algebra. So it's just a restatement, but it's a convenient restatement because sometimes it's more convenient to check this opposite inequality greater than n than less than or equal than n. For example, in the next property, okay, we say that if you have several stopping times, then their minimum and their maximum is also a stopping time. So if tau 1 up to tau n are stopping times, then the minimum over k less than or equal than n of tau k, as well as the maximum, are also stopping times. Okay, this is convenient. For example, if you want to have some integrability conditions, you can simply truncate your random variable at some large constant value, because the first property is that a constant is a stopping time. So if you take a minimum of some stopping time and a very, very large constant, that's also a stopping time, which can be convenient. Okay, and of course, how do you prove this? Well, for the maximum, you just check by definition that if the maximum is less than or equal than n, that means that each one is less than or equal than n. So it's just an intersection of the events that tau k is less than or equal than n. Right? Each of these is in Bn by the definition of stopping time, so the intersection is also in Bn. And for the minimum, it's convenient to check the opposite inequality, right? That this is greater than n, the minimum is greater than n, again, if and only if each of these tau k is greater than n. And now the intersection is in the sigma algebra, so you get that this is also a stopping time. So the next property is if you have two stopping times, then their sum is also a stopping time. Okay, and I need to check this here. It's convenient to take, for example, the equality definition for the stopping time, because the sum is equal to n. You can write this as a union from k over k from 0 to n, that the first one is equal to k, and then the second one must be equal to n minus k. Right, and then the event in bk and n minus k, by the increasing property of your sigma algebras, are both in bn, so you get what we want here for the sum. Now, another observation is that if you have a couple of stopping times, you have the sigma algebras associated to them. We already checked that the stopping time is measurable with respect to that sigma algebra. But another observation here is that when you compare two stopping times, let's say, by strict inequality or by an equality, or you can take a non-strict inequality, because it's just the union of these two previous events, right? So all of these will be both in the sigma algebra associated with the first stopping time and with the second stopping time. Now I'm going to leave this one and the next couple of properties as an exercise, so I'll just state them here. The next one is that if you have an event in the sigma algebra corresponding to this first stopping time, then the intersection of this event with the event that this first stopping time is bounded by the second stopping time is in the sigma algebra corresponding to the second stopping time, and the same with the strict inequality. Now, of course, by the previous property number 6, we already know that both of these intersections are also in b tau 1, right? Because the b is in b tau 1 and the comparison of two stopping times is in b tau 1. But here we also know that this type of intersection, when you kind of compare on the event where the second stopping time is bigger, you also end up in the second sigma algebra corresponding to the second stopping time. And finally, if your one stopping time is less than another stopping time, then the sigma algebras are also increasing. So this increasing property is preserved. Okay, so these are the basic properties of stopping times that are very convenient just to summarize from the very beginning, and then next we'll discuss this optional stopping theorem. Right, so what we are going to prove in this optional stopping theorem is that when you consider a martingale and you consider any increasing sequence of stopping times, then the values of your martingale at those stopping times will again form a martingale. Let me just write down that if we consider a sequence which is a martingale, okay, and in this particular case it's really convenient or useful to think of this as a fair game. And then we consider some stopping times. So these are decision rules for possible decision rules for stopping the game. So let's say stopping times tau1, tau2, and so on. And these stopping times come with their sigma algebras as we defined above, which by the last property above, it's going to form an increasing sequence of sigma algebras. Okay, then what we want to show basically is that your martingale at these random times with these sigma algebras will also form a martingale. Okay, but of course under some integrability conditions. And you can think of this as the fact that a fair game stays fair under any stopping rules. So you can evaluate the sequence at random times as long as those times are decision rules that do not look into the future, then your sequence will still have this property that conditionally on the data up to that stopping time, the value at any future stopping time will still on average be what you see right now. Now let me state the theorem more precisely with precise assumptions that we will have on these stopping times. So the theorem will say the following, that if you have a martingale xn bn, okay, and of course we only need to consider two consecutive stopping times to prove the statement that I just mentioned. So let's say tau1 less than or equal to tau2 are both stopping times. And then the integrability condition will be the following. Will actually be two conditions. One is that the expectation of the process at the second stopping time is integrable. And this is kind of a necessary condition if we want to talk about x evaluated at stopping times as a martingale. So we need this to be integrable anyway. And then the second condition, integrability condition, will be that the expectation of xn, the absolute value of xn, on the indicator when the second stopping time exceeds n, okay, that this will become small as n goes to infinity, right? So this will go to 0 as n goes to infinity. You know, it's kind of a technical condition, and we'll see that you need some kind of integrability condition of this form. So we'll see it in a couple of different ways in a second. But under these conditions, we'll conclude that indeed this is a martingale. So I'm just going to write out more precisely the definition of what it means to be a martingale, or what the conditional expectation means here, right? It means that for any set in the sigma algebra corresponding to the first stopping time, when you average x at the second stopping time on this set, it's the same as averaging x at the tau1 on this set, right? Of course, this is nothing but saying that expectation of x tau2 conditionally on the data at time tau1 is x tau1, right? So that's the statement of the theorem. Now, before we prove this, let me make a couple of comments here. So the first comment is, what if the stopping times are not necessarily ordered? So, you know, maybe what if you don't have this inequality? Maybe sometimes one stopping time is greater, sometimes another one is greater. Then you can simply rephrase the above conclusion of the theorem in the following way. You can just add the indicator that tau1 is less than or equal than tau2. So the equation above in this case can be replaced by expectation of x at tau 2 on the set A, and also on the set where tau 1 is less than or equal than tau 2 is the same as expectation of x tau 1 times this indicator, again conditionally, or on this set where tau 1 is less than or equal tau 2. Okay, so you can state this slightly more general statement, but it's really an immediate consequence of the above statement. Actually, in the proof, the way the proof goes, in a sense, we'll be proving this more general statement anyway, so I'm not going to describe this reduction in detail, but you can check that if you can simply consider a stopping time tau, which is the minimum between these two stopping times, tau 1 and tau 2. So in particular, you enforce this inequality that tau is less than tau 2. And then you can apply the conclusion of the above theorem to this new set with this additional intersection, tau 1 less than or equal tau 2, and you can see that the statement of the theorem applied to this new set. I mean, first of all, you will have to check that this new set A intersection with this condition tau 1 less than or equal than tau 2 is in B tau 2. So if you check that this holds and apply the statement of the above theorem to this set, you will recover this more general looking statement. Okay, so that's one quick comment. But another comment that I wanted to make is kind of a famous example which shows that you do need some kind of integrability condition. Okay, and this comes from the following classical example, that if you consider a sequence of random variables, independent random variables, with the following distributions, that xn takes values plus or minus 2 to the n with equal probabilities 1/2. Okay? And you consider sigma algebra generated by this sequence. Then, since the expectation of these random variables is 0, the sum will be a martingale, as we saw before. Right? So that Sn Bn is a martingale. Now, if you take the stopping time tau 1 to be just a constant 1, and then take tau 2 to be the first time when the sum becomes strictly positive. Okay? And what this means here, of course, you can notice that if you add up the first few values which are negative, so let's say up to time k minus 1, your outcomes were negative, then the first positive outcome, let's say if it happens at time k, actually the whole sum will be just equal to 2. So the first time the sum becomes positive, it's the first time the sum becomes equal to 2, or the first time you see a positive outcome in the sequence x. But this 2 is also, it will be exactly the value of your process at time tau 2, right? For this reason. And you can see that if you apply the above theorem, you do not have that this equality, that conditional distribution of the sum at time tau 2 is equal to tau 1, because even their expectations will not be equal, right? So your expectation of s at tau 2, well, it's 2, and it's not equal to 0, which would be the expectation of s at tau 1, right? Which is just expectation of x1. And the reason for this is that the second condition does not hold. Of course, the first condition holds, that the martingale at the second stopping time is integrable because it's just equal to 2 here. But the second condition, that expectation of the martingale at time n on the set where the second stopping time is greater or equal than n, this should go to 0, but here it does not go to 0, as you can see, because you can have two possibilities: that the stopping time is actually equal to n, then the sum is 2, so 2 times the probability that the stopping time is equal to n, or the stopping time tau2 is greater, strictly greater than n. But if it's strictly greater than n, that means that all the values up to that time had the same sign. And so when you add them up, you'll just get 2 to the n plus 1 minus 2, right? Because we take absolute value. So this is on the event that tau2 is strictly greater than n, or greater or equal than n plus 2. And we know the probabilities for this, because we already saw that for the stopping time to be equal to n, you must have precise outcome at every step. And all of them happen with probability 1/2, and they are independent, so you get 1 over 2 to the n for this value. And then for the second probability, you just add up 1 over 2 to the k from n plus 1, and you get another 1 over 2 to the n. And you can see that this simplifies to 2, so this does not go to 0. Okay. So in this particular case, although the sum forms the martingale, the individual terms in this sum, they become too large fast, so you don't have control of what's going on in the tail. So without some kind of integrability condition, you do not have this kind of optional stopping theorem. So that's the second comment, and now we can proceed to the proof of this optional stopping theorem. Okay, so we take a set in the sigma algebra up to time tau1, and then we want to calculate the expectation of x at time tau2 on this set, or somehow we want to simplify this. All right, as usual, when we deal with stopping times, we are going to sum over all the possibilities here for the first stopping time. So we are going to fix the value of the first stopping time. So we'll sum over all n, expectation of x tau2, indicator of a, and let's put an indicator that tau1 is equal to n. Okay. And so here we have a product of indicators, so we have the set A intersected with the set tau1 is equal to n, and by the definition of the stopping time, right, we know, because here the set A comes from the sigma algebra corresponding to the stopping time tau1. By the definition, this intersection must be in Bn. Okay, so we know this, and for simplicity of notation, let's denote this set An for a second. We also know that tau2 is greater than tau1, so on this particular set, right, when tau1 is equal to n, we also know that tau2 is greater than or equal than n. Okay, so we can add that condition if we need to add or remove it. And what we'll do with this second condition is we are going to approximate it by the condition that tau2 is in between n and some large number m. So, we are going to consider this expression as above, so with all these indicators, and again, the intersection of two indicators, I just denoted that set by an, right? And then I'm going to put this indicator that n is less than or equal than tau2, which is it's for free, it doesn't change anything. But if you add some bound from above, then this is only true in the limit. So it converges to the above when m goes to infinity. And I also want to conclude that expectation of this converges to the above expectation, right? And this is true by the first assumption. So we had this assumption that expectation of x at tau 2 is finite, right? So that gives us the dominated convergence theorem. So by dominated convergence theorem, we have convergence of this expectation for a given term in the sum. So I'm considering just fixed n here. Right? So we can approximate an indicator by a truncated second stopping time at some n. All right, and then we are going to write this expectation here as a sum over the second stopping time. So we'll take a sum from n to m minus 1, right? The expectation of x tau 2, but since I'm going to force tau 2 to be equal to k, I'm just going to write this here, xk. And so indicator an, an indicator that tau 2 is equal to k. So I'm just writing up as a sum over specific values for tau 2. And the main trick in this proof is to write this indicator as the following, as the same difference of indicators that we wrote above. So namely indicator that tau 2 is actually, this is a little bit different here, that indicator that tau 2 is greater or equal than k minus indicator that tau 2 is greater or equal to k plus 1. And then we are going to break this into this difference of two integrals. But in the second one, we will notice that when we consider the set here, tau 2 greater or equal than k plus 1, this is actually in the sigma algebra bk, right? Just like we have seen before, because the complement of this set is tau 2 is less than or equal than k. So that's in bk. And also let's notice here that the set an is also in bk, because the k here, we consider k starting from n and greater than n. So by inclusion, an is also in bk. So the set an intersected with this set in the second term, right? It's going to be in bk. And so when we break this sum into 2, so the first term we'll just leave it as it is. But for the second term, we use the fact that x, the sequence x, is a martingale. So we are going to actually replace xk by xk plus 1. Right? Because the indicators here belong to bk, so the average of the next random variable in our martingale sequence at time k plus 1, on this set it's the same as average of xk. So here we replace xk by xk plus 1 using the martingale property. And this is kind of the main trick to go from this term to this term here, or from the second term above to this term here, because now we created a telescopic sum. And so in this sum, only the first and last term will survive when you add them up. So you'll get expectation of xn, and then you'll get the last term . The first term here, you can again, if you wish, you can erase the last indicator because it's already included in the set an as we said above, because set an already contains the fact that tau1 is equal to n and tau2 is greater or equal than tau1. So you can erase the second indicator if you like. And then for the second term, we use the second assumption, right? So this will go to 0 by the second integrability assumption. Because if you look at that assumption, it's actually saying that with absolute values, this function will, the integral of this function will go to 0 when m goes to infinity. Okay, so this term disappears by the second assumption. Okay, and then if you look at everything we just did by approximating by this truncation, right? We just showed that the expectation of x tau2, indicator of this set A, intersected with indicator that tau1 is equal to n, right? We just calculated this and showed that this is equal to expectation of xn, indicator of the set an, which is again indicator of A times indicator that tau1 is equal to n. Right? And so if we go back to what we started, where we just sum the expectation of x tau2, indicator of the set A, over all possible values of tau1, right? Now we can rewrite it as a sum over n of the right hand side above, so expectation of xn, indicator of A, indicator of tau1 is equal to n, right? And of course now you can just replace here xn by tau1, and you get expectation of x tau1, and you sum over all indicators, so you just left indicator of A. All right, of course, maybe something I haven't mentioned above as an implicit assumption, we always had the assumption that these stopping times are proper, right? So in this calculation, when we sum over all values of the stopping time, we really mean that infinity is not allowed here. So maybe I should emphasize that tau1 and tau2 are proper stopping times. So they are less than infinity with probability 1 in the statement of this theorem. Okay, but this finishes the proof of this optional stopping theorem. Now, one quick remark here that I wanted to make is that in this calculation, this last calculation where we used this telescopic series trick, if you take, so it will be convenient to consider a specific case here. So let me emphasize this as a remark, that if in the above calculation we take, tau1 to be just 0, and the set A over which we integrated, let's take the whole space, so we don't need to write that indicator. Then in the above calculation, we basically showed that one can write the expectation of x0 when you write this telescopic sum as expectation x tau2 on the indicator that tau2 is less than m, plus expectation of xm on the indicator that tau2 is greater or equal than m. Okay, that's exactly the above calculation between 0 and some fixed value m, when the set A is just the whole space, so there is no indicator. Okay, I just want to emphasize here, because this is kind of convenient if you just want to compare the expectation instead of conditional expectations. So in particular, what this says that, if you want to send this m to infinity, then you get that the expectation of x0 is equal to this limit when m goes to infinity of the expectation of x at some stopping time on the indicator where that stopping time is less than m, this is if and only if the second term goes to 0, right? That the limit when m goes to infinity of the expectation of xm on the indicator that m is less than or equal than tau2 is 0, right? So you have a little bit cleaner condition without absolute values. So if you just want to compare expectations, then you have this clean statement from that proof. And in particular, if you know that, if you know some additional assumptions on the integrability, you would, of course, the same assumption, let's say, as above, you would, of course, recover simply the statement that the expectations are the same. Okay, but here we get this more precise and clean statement for the expectations using the above calculation, where we use this telescopic series trick, right? So, without any reference to other integrability conditions, you can have this kind of statement for comparison of the expectations. Okay, so that's the optional stopping theorem, and next we are going to take a look at random walks and look at some application of this optional stopping theorem to random walks.